Alright, in this video we're going to look at some examples where we're just going to convert different numbers of moles to number of particles or number of particles to moles. Just get used to using that equation. We're always going to do things both ways. We'll quickly use the equation or the factor reduction method after we do it. One way we'll do it the other way really quickly just to make sure, just to show how they're the same. So in a liter of water there are about 55 moles of water. So we're saying that our moles of H2O. Subscripts are nice here because they're going to help us keep different substances straight. About 55 moles of water in a liter. How many water molecules are there? How many molecules of water are there in a liter? That makes more sense. So what we want to do here is we want to get the number of particles. Okay? The equation that I said is that moles is equal to the number of particles divided by Avogadro's number. So substituting 55 moles is equal to the number of particles. Avogadro's number 6.02 times 10 to the 23. And then so my number of particles is 3.311, I guess I should have been able to figure that one out, times 10 to the 25 particles. So that's using the equation, that's fine. I multiply both sides by 6.02, get it up to the other side, they end up multiplying together. Using the factor reduction method, I would have said I have 55 moles. I want to convert moles to particles. So for every 1 mole I have 6.02 times 10 to the 23 particles, and so 55 times 6.02 is 3.311 times 10 to the 25 particles. You can take either approach, whichever you feel more comfortable with, equations or factor reduction. How many moles of iron are there in 1.5 times 10 to the 25 particles of iron? So here we have our number of particles, which is going to be 1.5 times 10 to the 25 particles. And I'd like to express that as a number of moles of the iron that we're talking about here. Using the equation, I can say that the number of moles of iron is equal to the number of particles divided by Avogadro's number, which is 1.5 times 10 to the 25 particles, divided by Avogadro, 6.02 times 10 to the 23 particles per mole. And so that works out to 24.9 moles. So that's one way to get there using the equation. You could also use the factor reduction method. So I got 1.5 times 10 to the 25 particles, that's 225 particles. And I want to convert my number of particles into a number of moles. For every 1 mole, there's 6.02 times 10 to the 23 particles. And now I can see I have a number on the top, and this is on the bottom. And remember, if something's on the bottom of a fraction, that just means divide. So if I go 1.0 or 1.5 times 10 to the 25 divided by 6.02 times 10 to the 23, same calculation as before, of course, because these two methods are consistent, but just a different way of thinking about it. I'm still getting 24.9 moles. All right. Last example for this video, I'm going to use a mole ratio in this example to figure out how many actual hydrogens there are in a molecule of water, a set amount of it. So there are 55 moles of water molecules, so that's H2O molecules. How many hydrogen atoms are there? So if I think about breaking this into, so if we have H2O, this isn't what really would happen, right? These aren't real molecules that are being formed here. But if we imagine breaking that down into the hydrogens and oxygens that make it up, for every one molecule of water, there would be 2 atoms of hydrogen. So the ratio for the moles of water to the moles of hydrogens is 1 to 2. So that's our mole ratio, right? I use the actual coefficients of, most of the time it'll be a balanced chemical reaction. But in this case, since I'm just interested in atoms, I'm just really using a reaction to show how many of each kind of atom I have. And then with that, I can convert my number of moles of water into a number of moles of hydrogen atoms specifically. Here I have 55 moles of water particles. So, that shouldn't be H2O, so it should be H. How many moles of hydrogen do I have? And here I'm going to bring the NH up here. The 2, multiply both sides by 2, and I get 110 moles of hydrogen atoms. You can do this as well using the factor reduction method. Here I have moles of H2O, and I want to convert those. So I have 55 mole H2O, and I want to convert that into mole H. So I cancel out my moles of H2O and my moles of H, so in 1 mole of H2O I get 2 moles of H. That cancels that, and I can think of this as a conversion as well. And I still get 110 moles of hydrogen. So mole ratio or conversion, either way is fine. Now we have to convert that actual number of moles into a number of particles, I think. It said how many hydrogen atoms. So, again, I can use my formula. Number of particles divided by Avogadro's number. So here, my 110 moles is going to be equal to some number of particles for hydrogen divided by Avogadro's number. So I can get my number of particles by multiplying those two things. So I get 6.622 times 10 to the 25 hydrogen atoms. Or if I want to view this as a conversion, I can recognize that I'm converting 110 moles of into particles. I need to cancel out my moles. And in every 1 mole, there's 6.02 times 10 to the 23 particles, which means I'm going to end up with 6.622 times 10 to the 25. And that will be my number of hydrogen atoms. Again, I'm going to keep doing both here all the time, keep showing you both ways of thinking about it. Doesn't make any difference which one you actually use, but I want to make sure that I'm being flexible so you can hopefully see it in as many different ways as possible. So that's just some examples for working with moles.